Bismillahirrahmanirrahim. Assalamu alaikum. In this video, we shall study the Laplace transform. Some of the contents of this lecture are given on the screen. In addition, we shall solve several questions to explain the concepts. Let us see the definition of Laplace transform. The Laplace transform of a function f of t is denoted by capital F of s or L of f of t, and it is defined by this formula. Laplace transform of f of t is equal to integration from 0 to infinity f of t e power minus st dt. So this is the basic formula which we shall use to find Laplace transform of different functions. Let us start from question number 1. Find the Laplace transform of 1, number 2 t, number 3 t square, number 4 t cube. Let us solve question number 1. To solve part number 1, here f of t is equal to 1. So put f of t is equal to 1 in formula number 1. Then formula number 1 implies that Laplace transform of 1 is equal to integration from 0 to infinity 1 n to e power minus st. So we can see that we just put f of t is equal to 1 on both sides of formula number 1. And now we have to just integrate, but this is improper integral. So you can also take limits h approaches to infinity and replace infinity by h, but we are using direct formulas. So integration of e power minus st is e power minus st divided by minus s, and the limits are from 0 to infinity. And now let us take minus 1 over s outside of the bracket. So we can write this 1 over e power st, and let us put the limits which are from 0 to infinity. Now put the above limit. So 1 over infinity, e power infinity is infinity, and minus 1 over e power 0 is 1. So from here we can obtain that this is minus 1 over s into 0 minus 1. And if we simplify this, we get that Laplace transform of 1 is equal to 1 over s. So this is the main formula of Laplace transform of 1. Part number 2 is to find Laplace transform of t. So let us write Laplace transform of f of t, which is the basic formula, equal to integration from 0 to infinity f of t e power minus st dt. And now let us put f of t is equal to t. So we have Laplace transform of t is equal to integration is from 0 to infinity t n to e power minus st dt. Let us use integration by parts. So we can have first function integration of the second function, and limits are from 0 to infinity, minus integration differentiation of the first function into integration of the second function dt. And now from here we can obtain that Laplace transform of t is equal to taking minus 1 over s outside of the bracket, and here we have t divided by e power st, and the limits are from 0 to infinity, and this one is now plus 1 over s. Integration is from 0 to infinity e power minus st dt. And now you can see if we put infinity, this is infinity by infinity form. So we can use the L'Hopital rule here. If we use the L'Hopital rule, we can get 0, and now minus. If we put 0, again we have 0. And from here, this is plus 1 over s, and integration of e power minus st is given by this thing. Limits are from 0 to infinity. This is equal to minus 1 over s square. And now let us put limits. So if we put limits, you can write that this is 1 over e power st. The limits are from 0 to infinity. So this can be written as minus 1 over s square into e power infinity is infinity, anything divided by infinity is 0, and e power 0 is 1. So we have from here that Laplace transform of t is equal to 1 over s square. That is the basic formula for the Laplace transform of t. Now let us solve part number 3, in which we have to find the Laplace transform of f of t is equal to t square. So using f of t is equal to t square in the basic formula, we have integration from 0 to infinity t square e power minus st dt. Again here we shall use integration by parts. So we have first function into integration of the second function, and the limits are from 0 to infinity, minus integration differentiation of the first function, which is 2t, integration of the second function e power minus st divided by minus s dt. And now if we further simplify this by putting the limits, we can see we get 0 minus 0, and minus, let us take 2 over minus s common, so this is plus 2 over s, and here we have 0 to infinity t e power minus st dt, and we can see that this is Laplace transform of t. If we put f of t is equal to t in the basic formula, we can easily get that Laplace transform of t is this thing. But we have already obtained, let me write it here, we have already obtained the Laplace transform of t, which is 1 over s square. So from this we can write 2 factorial divided by s cube. So we can say that Laplace transform of t square is equal to 2 factorial divided by s cube, and that is the required formula for the Laplace transform of t square. Now the fourth part is to find Laplace transform of the function f of t, which is equal to t cube. So let us use t cube in the basic formula. We have Laplace transform of t cube, which is equal to integration from 0 to infinity t cube e power minus st dt. Let us use integration by parts. So we have first function integration of the second function. The limits are from 0 to infinity, minus integration, differentiation of the first, integration of the second into dt. And now if we apply the limits, we can see we will get 0 minus 0. For the first term, this is obtained by using the L'Hopital rule. Minus, taking 3 over minus s common, so we have 3 plus 3 over s, and now we have 0 to infinity t square e power minus st dt, and we can see that this is 3 by s, and the remaining is Laplace transform of t square. If we use t square on both sides in the basic formula, we can easily obtain that Laplace transform of t square is this thing. So this is equal to 3 by s, and Laplace transform of t square we have already obtained, which is 2 factorial divided by s cube. So from this we can write that Laplace transform of t cube is equal to 3 factorial divided by s power 4, and that is the required rule for the Laplace transform of t cube. In a similar procedure, now we can write that Laplace transform of t power 4 must be equal to 4 factorial divided by s power 5. And if we further generalize this, we can write that Laplace transform of t power n is equal to n factorial divided by s power n plus 1. So this is the general rule for the polynomials. Question number 2. To find the Laplace transform of e power at, let us write the basic formula of Laplace transform, which is given by integration from 0 to infinity f of t e power minus st dt. Now put the value of f of t on both sides of this formula. We have Laplace transform of e power at is equal to, integration is from 0 to infinity, e power at n to e power minus st dt, and this can be written as 0 to infinity e power a minus s into t dt. Let us integrate this. We have e power a minus s t divided by a minus s, and the limits are from 0 to infinity. Now, under the conditions that s is greater than a, let us take minus as common. So we have s minus a t divided by a minus s, and the limits are from 0 to infinity. From this we have, taking 1 over a minus s outside of the bracket, we have 1 over e power s minus a into t. Limits are from 0 to infinity. This is equal to 1 over a minus s. And now if I put infinity, I get 0. Minus if I put 0, I get 1. So we have minus 1 over a minus s. But we know that s is greater than a. So let us write this as s minus a. So from this we have 1 over s minus a. So the Laplace transform of e power a t is equal to 1 over s minus a when s is greater than a. And this is the fundamental rule for the Laplace transform of e power a t. Question number 3. Find the Laplace transform of cos at and then sin at. Let us solve part number 1. Here f of t is equal to cos at. Let us use the basic formula of Laplace transform, but take f of t equal to cos at. Then it is equal to integration from 0 to infinity cos at into e power minus st dt. Now let us put I equal to integration from 0 to infinity cos at into e power minus st dt. Let us say this is equation number 1. And now we have to use integration by parts. So we can write first function cos at integration of the second function, and the limits are from 0 to infinity minus integration differentiation of the first. This is a sine at, but differentiation of cos is minus sine, so I write it as plus, and e power minus st divided by minus s dt. Now from here we can write that this is cos a t divided by e power st, taking minus 1 over s outside of the brackets. The limits are from 0 to infinity. And now taking a over s minus a over s outside of the integration, we have sine at e power minus st dt. Limits are from 0 to infinity. Now again we will apply integration by parts. From the first term you can see we can write minus 1 over s, and now e power infinity is infinity, anything divided by infinity is 0, minus cos 0 is 1, e power 0 is 1, so we have this thing, minus a over s into first function sine at integration of the second e power minus st divided by minus s. Limits are from 0 to infinity minus integration 0 to infinity differentiation of the first. So it is a cos at integration of the second, and we have dt here. Now let us simplify this. From here we can get 1 over s, and minus a over s into. Now again, if we divide by infinity with 0 and sine 0 is 0, so from this term we get 0. Now minus a over s can be taken as constant outside from the bracket, and we have a divided by s, and this is now 0 to infinity cos at e power minus st dt. From this we can get that I is equal to 1 over s. Let us multiply minus a over s, so we have minus a square divided by s square, and integration is from 0 to infinity cos at into e power minus st dt. But we can see from 1 that this thing is equal to I. So I will write I is equal to 1 over s minus a square divided by s square into I. I will write from 1. From 1 we can see this term is equal to I. Now taking I to the left hand side, we have I minus a square divided by s square, so it will become plus here. I is equal to 1 over s. And now from here, let us take I as common and taking LCM. So LCM is s square. So we have s square plus a square is equal to 1 over s. And from this we can obtain I is equal to 1 over s into s square divided by s square plus a square. Now from this we can get cancelling 1s with 1, we have I is equal to s over s square plus a square. Now let us put this value. So we have Laplace transform of cos at is equal to s over s square plus a square, and that is the required solution for this problem. In a similar procedure, if we want to prove that Laplace transform of sine at, we will write in the basic formula. Integration is from 0 to infinity sine at into cos at is sine at, and now I'm using the basic formula, so this is e power minus st dt. Now represent this by I, and in a similar way like part 1, you can obtain that Laplace transform of sine at is equal to a divided by s square plus a square. So we should remember these formulas. Let us study two properties of the Laplace transform. The first one is called constant preserving property, which means if a constant a is multiplied with a function f of t, then the Laplace transform of this is equal to a Laplace transform of f of t. The second property is called the linear property, which says that Laplace transform of a f of t plus r minus b g of t is equal to a Laplace transform of f of t plus or minus b Laplace transform of g of t. Here a and b are real constants. And now let us solve question number 4. To solve part 1, here we can write that cos hyperbolic at is equal to e power at plus e power minus at divided by 2. And now let us take Laplace transform of both sides. So we have Laplace transform of cos hyperbolic at is equal to Laplace transform of e power at plus e power minus at divided by 2. And now let us use the linear property, which says take 1 over 2 common and find Laplace transform of e power at plus Laplace transform of e power minus at, which we have proved that Laplace transform of e power at is 1 over s minus a plus Laplace transform of e power minus at is s plus a. And now let us take LCM. So we have 1 over 2 into the LCM is s square minus a square. And here we have to write s plus a minus, sorry, this is plus s minus a. And now let us simplify. Minus a and plus a, they will cancel. So we have 1 over 2 into 2s divided by s square minus a square. 2 will cancel with 2 and we get that the Laplace transform of cos hyperbolic at is equal to s divided by s square minus a square. So that is the basic formula for the Laplace transform of cos hyperbolic at. To solve part 2 in a similar way, we can write sine hyperbolic at, which is equal to e power at minus e power minus at divided by 2. And in a similar procedure like part 1, we can prove that Laplace transform of sine hyperbolic at is equal to a divided by s square minus a square. So that is the basic rule for the Laplace transform of sine hyperbolic at. Property number 3. This is called the first shift property, which says that if Laplace transform of f of t is equal to capital F of s, then the Laplace transform of e power at into f of t is equal to capital F of s minus a, which means that if we have to find the Laplace transform of e power at into f of t, the first step is to obtain the Laplace transform of f of t, which will be f of s. And now just subtract this a from any s in the solution of Laplace transform of f of t. So we will get f of s minus a. Let us solve question number 5. Find the Laplace transform of e power 2t into t cube and e power 3t cos phi t. To solve part number 1, here f of t is equal to t cube. And now let us find its Laplace transform. So Laplace transform of t cube is equal to 3 factorial divided by s power 4. Now to find the Laplace transform of this product, which is e power 2t into t cube, we have to just subtract 2 from s. So the solution is 3 factorial divided by s minus 2 whole power 4, and that is the required solution of this problem. Let us solve problem number 2, part number 2. Here f of t is equal to cos phi t. And now we know that the Laplace transform of cos phi t is equal to s divided by s square plus phi square, which is 25. Therefore, the Laplace transform of this product, which is e power 3t into cos phi t, this is equal to, just subtract 3 from s. So we can write s minus 3 divided by s minus 3 whole square plus 25, and that is the required solution for this problem. Now let us see the definition of unit step function or Heaviside function. It is a function which is denoted by u of t and is defined by u of t is equal to 0 when t is less than 0 and u of t is equal to 1 when t is greater than 0. Now let us solve question number 6, in which we have to find the Laplace transform of u of t. So by the basic formula of Laplace transform, we can write Laplace transform of f of t is equal to, integration is from 0 to infinity, f of t e power minus st dt. But here f of t is u of t, so let us put the value of u of t. So we have u of t, which is equal to integration from 0 to infinity u of t into e power minus st dt. And now let us put the value of u of t. When t is less than 0, it is 0, but when t is from 0 to infinity, the value of u of t is 1 from the above definition. So we write this thing. And now let us integrate this. So if we integrate this, we have e power minus st divided by minus s. And the limits are from 0 to infinity. Let us take minus 1 over s outside of the bracket, and we can write 1 over e power st, and limits are from 0 to infinity. So we have minus 1 over s, and when we put infinity, we get 0. When we put 0, we get 1. So we can see that the Laplace transform of the unit step function is equal to 1 over s. So that is the basic formula for the Laplace transform of u of t. The shift unit function is denoted by u of t minus a with shift a and is defined by u of t minus a is equal to 0 if t is less than a. And this is 1 when t is greater than a. Question number 7. Find the Laplace transform of u of t minus a. So here f of t is equal to u of t minus a. And now let us write the basic formula for the Laplace transform of f of t, which is equal to integration from 0 to infinity f of t into e power minus st dt. And now if we put the value of f of t, which is u of t minus a, we get that this is equal to 0 to infinity u of t minus a into e power minus st dt. And now we can see that from 0 to a, the value of u of t is 0 into e power minus st dt. And if we take from a to infinity, the value of u of t minus a is 1 e power minus st dt. So this can be written as the first term is now 0 and the second term is from a to infinity e power minus st dt. Let us integrate this. So we have Laplace transform of u of t minus a is equal to, integration is from e power minus st divided by minus s. This is the integration, and the limits are from it is from a to infinity. Now let us take minus 1 over s outside of the bracket, and we have 1 over e power st. The limits are from 0 to infinity. This is from a to infinity. Now if we put infinity, we get 0. Minus if we put a, we have e power as. So if we simplify this, we get that Laplace transform of u of t minus a is equal to e power minus as divided by s. So this is the general formula for the Laplace transform of u of t minus a. For example, if we have to find Laplace transform of u of t minus 4, what we will write? So this will be equal to e power minus 4s divided by s. That will be the required solution. Property number 4. This is called the second shift property. It states that if the Laplace transform of a function f of t is equal to capital F of s, and u of t represents a unit step function, then the Laplace transform of f of t minus a into u of t minus a is equal to e power minus a s f of s, where f of s is the Laplace transform of f of t. Now let us solve question number 8. Find the Laplace transform of t minus 3 into u of t minus 3. To solve this problem, here we can see that f of t is equal to t. And if we take the Laplace transform of f of t, which is t, then this is equal to 1 over s square. And now let us find the Laplace transform of t minus 3 into u of t minus 3. So according to the second shift property, this is equal to e power minus 3s into Laplace transform of f of t, which is 1 over s square. So the given solution is e power minus 3s divided by s square. That is the required solution of this question. Property number 5. Let the Laplace transform of f of t is denoted by capital F of s. Then the Laplace transform of t power n f of t is equal to minus 1 power n nth derivative of capital F of s. Now if we put n is equal to 1, we get this result. If we put n is equal to 2, we get this result, and so on. Using this property, let us solve question number 9. Find the Laplace transform of t square sine 2t. Let us say here f of t is equal to sine 2t. And now if we take Laplace transform of f of t, which is sine 2t, then we know that this is equal to 2 divided by s square plus 2 square, which is 4. So now we can easily find the Laplace transform of the given question, which is t square sine 2t. So according to rule number 5 or property number 5, this formula, we can write minus 1 power 2 d2 over ds square of 2 over s square plus 4. Let us say we can write this minus 1 square is plus 1, so we can write that this is d square over ds square of 2 into s square plus 4 whole power minus 1. And now let us say this is 1. We represent g of s is equal to 2 into s square plus 4. And now let us differentiate this. So g dash of s is equal to minus 2 into s square plus 4 whole power minus 2, and our differentiation is 2s. So we can write that this is minus 4s into s square plus 4 whole power minus 2. Let us differentiate it once again. So g double dash of s is equal to minus 4. And if we differentiate this by using the product rule, we have first function, differentiation of the second function, s square plus 4 whole raised to power minus 3 into 2s plus second function, which is s square plus 4 whole raised to power minus 2. Differentiation of the first function, which is 1. And now let us simplify this. So we can write minus 4. Now 2 2s are is minus 4. So minus 4s square divided by s square plus 4 raised to the power 3. And this one is now plus 1 over s square plus 4 whole power plus 2. And if we take the LCM, we can write from here, the LCM is s square plus 4 whole cube. So here we can write minus 4s square, and here we can write plus s square plus s square plus 4. And now let us simplify this. So if we simplify this, we can get minus 4 into minus 3s square plus 4 divided by s square plus 4 whole cube. And now if we put this value in 1, we get 1 implies that Laplace transform of t square into sine of 2t is equal to minus 4 into minus 3s square plus 4 divided by s square plus 4 whole cube. And that is the required solution of this problem. The differential formulas. Let us see the Laplace transform of f dash of t, f double dash of t, and so on. If we denote the Laplace transform of f of t by capital F of s, then the first formula is Laplace transform of f dash of t is equal to s f of s minus f of 0. The Laplace transform of f double dash of t, that is the second formula, is given by s square f of s minus s f of 0 minus f dash of 0. So we can see that the first two terms are obtained just multiplying these two terms with s and then subtracting f dash of 0. Laplace transform of f triple dash of t. This is the third formula, which is equal to s cube f of s minus s square f of 0 minus s f dash of 0 minus f double dash of 0. So again we can see that the first three terms are obtained just multiplying these three terms with s and then subtracting f double dash of 0. So if we have to obtain the Laplace transform of fourth order derivative of f, then that will be equal to multiplying these terms with s minus f triple dash of 0 and so on. Let us see the proof of the first formula. Here we use the basic formula for the Laplace transform, which is f of t is equal to 0 to infinity f of t e power minus st dt. And now let us obtain Laplace transform of f dash of t. So just replace f of t by f dash in the above formula. We have integration is from 0 to infinity f dash of t e power minus st dt. Now we use integration by parts. So let us say this one is first function and this one is second function. So we obtain first function integration of f dash, which is f of t, and the limits are from 0 to infinity, minus integration from 0 to infinity differentiation of the first, integration of the second. And now from here we can write f of t divided by e power st. The limits are from 0 to infinity, plus s 0 to infinity, e power minus st f of t dt. And now if we use the limits, we can see anything divided by infinity is 0. And if we put 0, we have f of 0 divided by 1. So this is f of 0 minus plus s. And now we can see that the second one is formula for Laplace transform of f of t, which we can easily see from 1. So I will write from 1 we have this. And if we just simplify this, we get Laplace transform of f of t is equal to s, and this Laplace transform of f of t is denoted by capital F of s minus f of 0. And this one is the required formula for the given function. Now to prove formula number 2, we use the above result, star. So from star we can obtain Laplace transform of f double dash of t. This is equal to, we can write s Laplace transform of f dash of t minus f dash of 0. And now we can write s, let us put the Laplace transform of f dash of t from star, which is equal to s f of s minus f of 0 minus f dash of 0. So if we simplify this, we get Laplace transform of f double dash of t is equal to s square f of s minus s f of 0 minus f dash of 0. And that is the second formula. In a similar fashion, we can obtain formula number 3 and so on. That's all.